Hello and welcome to the Unit 10 podcast on section 17.1. Today we're going to be talking about reaction rates. Mr. Sakaguchi,
And I am Mr. Lin.
here we go. There. Okay, so we express reaction rates like any rate. It's going to be change over time. Like for instance, rate of speed is change in distance over time. But for us, since we're talking about chemical reactions, we're talking about change in quantities of substance over time.
So in this case, it's going to actually be concentration. So we're going to be measuring the molarity of a substance, and as that changes over time. So this could be the rate of the reactant disappearing or the rate of the product being made. So both work. Remember that reaction rates are always a positive value. So for the consumption of a substance, the average rate is going to be negative quantity of change or negative delta molarity over time.
Yeah, for the reason why it could be either reactant or product is it really depends upon what's more convenient to measure, what's easier to measure.
Right.
So how do we determine reaction rates? There's no way to eyeball an a chemical equation and know what the rate is going to be. It has to be done experimentally, and it cannot be calculated from balanced equations themselves.
Right. So you actually have to run the reaction with a stopwatch, and you have to record the times that it takes. And for something like this, it's always good to have more than one data point. So it's best to have two or, if not more, reactions run, the same exact reaction run, and then you average out the change in concentrations over time.
And so you take the difference, and it'll be the slope of the line, basically.
Right.
And so you can see the units would be molarity over seconds, which is moles over liter per second, but this is a complex fraction, so this is what it turns out to be. So if you see that for some of the rates, don't be confused by that. So how do we calculate the average rate of a reaction? Basically, we can, depending on how much data is present, we can do this in a few different ways. So for instance, if we base it upon hydrogen, we would look at the difference in hydrogen concentration versus the change in time, and take the difference and divide. And so this is what it would be for hydrogen.
Right. Or you could also look at it as how much hydrochloric acid is being produced. So the change of your final amount of hydrochloric acid minus your initial amount of hydrochloric acid, and then change in time would be 4 seconds. And then divide and find out, and that's the rate of reaction for production of hydrochloric acid. And if you notice between the two numbers that the hydrogen gas being used up is half as much as the hydrochloric acid being produced. This makes sense if you take a look at the chemical reaction where for every 1 mole of hydrogen gas, 2 moles of hydrochloric acid are being produced. So that coincides with the reaction and our values in the data that the reaction rate of hydrochloric acid production is double that of hydrogen gas being consumed.
Now that won't always be the case. One thing to point out here is that in this case there happens to be a correlation between the stoichiometric amounts, but that isn't always going to be true.
Right.
So that's just something to keep in mind. There are some theories behind how fast reactions go, and one of the things that will influence how fast a reaction goes is based upon something known as the collision theory. And this is the idea that reacting particles must collide in order for them to react. And they not just need to hit into each other, they need to collide with a certain amount of force and in the right orientation.
Right. So it's possible for two molecules or two atoms to hit each other, but if it's not at the right angle, you're not going to get the desired product or any product at all. It has to be a certain degree of angle and a certain amount of energy.
You know, for instance, like in the air right now, you know, there's nitrogen atoms, molecules hitting each other, but they're not reacting and becoming anything different. So enough force, right orientation. There's also this idea that after a collision that has the proper energy and orientation occurs, that we're going to have something known as the activated complex. This is a transient arrangement of atoms that isn't reactants anymore, but not quite products yet.
Right. What it is it's an unstable intermediate step. So to get from point A to point B, there's a transition phase, and it's temporary. So be aware that these activated complexes exist, and it's the first step that leads towards our resulting chemical reaction overall.
So you can think of it as a way that the bonds are broken, but the new ones haven't quite formed yet.
Right.
There's also something known as activation energy. So this basically represents the minimum amount of energy that reactant particles must have in order to form a activated complex and lead to a chemical reaction.
Right. The activation energy is the startup energy necessary for the reaction to occur. If you have a high activation energy, then fewer of the fewer collisions that come about may not have enough energy for the reaction to occur. So you might wind up with a lower reaction rate. Whereas if you have a low activation energy, more of the particles that slam into each other will have the required energy to start the reaction, and so your reaction rate is going to be higher.
We can put all these things together into what we call an energy diagram. And so this represents the energy diagram for an exothermic reaction. So this represents, the y-axis represents the energy. So notice that the energy of the reactants is greater than the products. This is typical for exothermic reactions. This peak here represents the activation energy, and at the peak of the activation energy is where the activated complex is found. And what you find is that this would be the negative delta H, but notice that you'd also get your activation energy back.
Right. Another thing to keep in mind is that the products in an exothermic reaction, the products are lower in energy than the reactants, and that is, as a result, energy is being lost by our system. That's why it's in a lower position after the reaction.
For endothermic reactions, it looks a little bit different. Here, notice that the reactants have a lower energy value than the products. So notice how much higher the activation energy is for this one. And again, the one thing they have in common is that the activated complex is still at the peak. And then you get some of the activation energy back, but not all of it. And the result is that the energy is absorbed in the formation of the products.
Right. Notice that in both exo and endothermic reactions, the highest point of the graph is going to be the activated complex. The activation energy will always be the highest point of any reaction.
Spontaneity. Remember, if delta G is negative, it's spontaneous. If it's positive, it's non-spontaneous. Delta G has no influence on the rate. It can tell you whether it's spontaneous, but not if it's how fast or slow it's going.
Right. So you can have a slow, spontaneous reaction. An example of that would be a nail rusting. If you put an iron nail inside a glass of water, it's a spontaneous reaction of it rusting, but it will take a long amount of time.
And that's it, I believe.
Yeah.